Good afternoon. So let us continue with the hydrogen atom problem, which we just started yesterday. So the setting up of the problem is through a Hamiltonian that has exactly the classical form. So there is the momentum of, say, the proton or the nucleus with mass m1 plus momentum of the electron with mass m2 minus a Coulomb force, so a Coulomb potential which attracts the electrons and nucleus. And for generality, I will do a case where the positive charge is z, an integer, times e, and there is only one electron on the contrary. Okay? This describes not only the hydrogen, but also hydrogen-like ions like helium plus or lithium 2 plus or so. Okay? So when you strip all the electrons but one, you are essentially in a situation like this. Okay? So R1 is the position of the first, R2 is the second. Okay? And as in classical physics, you know that this two-body problem should be separated into center of mass and relative motion, because after all, the system is invariant by overall translations. Okay? And you certainly remember that you can introduce the center of mass R, which is m1 R1 plus m2 R2 divided by the total mass m, which is m1 plus m2. Okay? And the total momentum corresponding is simply the sum of the two. Okay? These, in quantum mechanics, become operators, but it's very simple to prove that these operators satisfy exactly the standard canonical commutation rule. So for instance, take any component of R and any component of total P and verify that this is just IH bar if the two components are similar, X and X, Y and Y, Z and Z, and zero otherwise. Okay? This is a very simple calculation. It requires splitting this into this four possible terms, but only this with this really gives contribution, and this with that. And when you sum the two pieces, m1 plus m2 over m really gives you a 1. Okay? It's a very simple calculation. Try. Okay? Another obvious quantity is the relative distance. It appears there. Okay? So it's, for instance, how do I write it here? R2 minus R1. Okay? So it's this distance vector R. The only less trivial thing is the relative momentum. One would be tempted to say, okay, a relative momentum is just a difference. Okay? So just P2 minus P1. But if you do so, you will notice something bad. You will notice that this relative momentum is not canonically conjugate to R in the usual way. If you try to calculate, say, any component of R with any component of P written in this way, you will not find IH bar delta alpha beta. And even worse, if you try to calculate the commutator of this relative momentum written in this way, notice this is wrong. With the center of mass coordinate, you will find something different from 0. You will find terms like m2 coming from here minus m1 coming from there, and the result is just not 0, which is bad also. Okay? So this object is not a good relative momentum because it doesn't satisfy the right commutation relationship. Okay? The solution to this problem is to put here two constants and try to determine them in such a way that the commutator are nicely satisfied. And once again, it takes very little algebra, which I urge you to do this afternoon or tomorrow, whenever you want. Just verify that the correct relative momentum here has the following mass ratios there, okay? M, again, is the total mass. So you have to put M1 over M in front of P2 and M2 over M in front of P1, okay? And once you do that, then everything is just fine. This commutes with that, and also this commutes with that. You can verify it, okay? I mean, this respects the usual commutation relationship. Now, it is in terms of this object that you can rewrite now everything, the Hamiltonian into P square over twice the total mass. This is the total momentum divided by the total mass, so it's associated to the center of mass motion, plus relative momentum square divided by twice the reduced mass, okay, where 1 over mu is just 1 over m1 plus 1 over m2, okay, minus z e square over r, okay? And now everything in here commutes with everything in here, and so the two parts of the motion, relative and center of mass, are nicely separated into a scheme that you can apply again separation of variables, as we explained last time, okay? So when you have separation of variables, the wave function is a product, and the energies are just, the energy is just the sum of the two energies, okay? So in principle, you can write the wave function, okay, in terms of r and r to be just a sum wave function for the center of mass times some relative wave function. And what is this, by the way? It's a plane wave, right? You might say, okay, but it's not normalizable. We have addressed this issue at length, okay? It doesn't really make. So there is here some total wave vector, some total k times r, appropriately rescaled if you need, okay? So this is very, very simple, and it provides a piece of kinetic energy which is center of mass motion, which is not important for us, okay? We're not going to discuss this any longer. The relative part has to satisfy this problem, on the contrary, okay? So this object, if I call this the relative Hamiltonian, okay, then this object should satisfy psi r equal to some E. We will see, we have to introduce labels. Let me, for the time being, be still generic and call them En and psi n, okay? Then we'll explicitly verify that this is really a certain triplet of quantum number related to angular momentum and so on, but for the time being, let's be generic, okay? So I solve this, okay, and obviously then this is a solution of the full problem with energy, okay, equal to this plus En, okay? So from now on, I will forget about center of mass, and I focus just on this problem in such a way that I have now a three-dimensional problem. Okay, so I now write this as, copying back here, p square over twice the reduced mass minus z e square over r. Okay, and I even omit the relative I mean this little r here. Okay, this is my important Hamiltonian. Okay, questions until now? This is very, very simple. Now this problem that I have to solve there, let me write it back. Can I erase here? Okay. Try to do this. Okay, it's simple but instructive. And also try to verify that you have to use this there. Otherwise, you don't get the initial Hamiltonian. So the problem I have to solve in principle is the following: p squared over twice the mass minus z e squared over r times some psi n of r equal to E n psi n of r. Now, this potential is an attractive potential of this type. Okay, this is r. So it goes to 0 for very large distance and to minus infinity there. Okay, so I could expect what? Bound states here, which we'll try to find, and obviously extended states here. This describes what? Not the electron bound to the nucleus, but the electron really going off the nucleus, I mean, making some scattering with a positive energy. Okay? So while these are kind of planetary motion type of things, these are like some asteroid passing by, okay, and going to positive energy far away. Okay? So these are unbound scattering states. These are bound states. Okay, we will not talk, in fact, about this. We will concentrate on bound states because those are the important ones, really, for our story. Okay. How do we study this problem? This is still a three-dimensional problem. This object here is the Laplacian in 3 dimensions. This is a potential 1 over r. Now, one thing that immediately jumps to your eye is that this depends only on the radial coordinate, while theta and phi, the angles that you can use to describe vectors in 3 dimensions, do not really appear in the potential. They do appear, however, if you write the Laplacian in spherical coordinates. So r, in principle, is not the only actor in this game. So we have to learn how to really separate r from theta and phi. And this is our next goal. Now, you have done this, by the way, with George Thomson. I have glanced today through the notes, which I found quite interesting. So, for instance, you should, I think, read chapter 11 of George Thomson notes. There are here and there many, many interesting observations, which I will not repeat here. I will try to briefly condensate the main points. Okay. So first of all, there is evidently a new object that you should account. The angular momentum has not been introduced until now because we were working with one-dimensional problems, but now we have 3 dimensions. You know that central potentials in classical physics conserve angular momentum. Let us introduce angular momentum, which, as in classical physics, has this expression, but now this is operator r and this is the operator p, and so this is an operator. Now, these operators obviously have 3 components, okay? So Lx, Ly, and Lz. Simple expressions. You have to do the vector product, okay? So, for instance, x is y pz minus zpy, and similarly, y is zpx minus xpz, and xpy minus ypx. Okay, these are the 3 expressions for the 3 components of this angular momentum operator. Now, at this level, it doesn't really matter if you put the y before, right? Because y and pz or z and py commute. So this is not the crucial thing. But whenever you ask, for instance, yourself if these two objects commute with each other, you will understand that they do not generally commute. And it is quite a simple matter, for instance, to show that they obey quite remarkable commutation relationship. They are so remarkable that you certainly have seen, but let me just very, very simply try to do the calculation. Okay? I want to prove to you that this is just I h bar Lz, the third one. Okay? And this, the calculation is very simple. You have to kind of get used to doing these things. So you just put here Lx, then you put Ly to be zpx minus xpz, okay? And then you start, you have four terms, for instance, this with that, okay? You have this with that. But notice that, for instance, when you consider this with that, all the quantities really commute because y, pz encounters x, which really is so this commutator is just 0, okay, no problem. Similarly, for instance, this object, am I doing the right thing here? Yes. Okay. Similarly, for instance, here, this term is not important because all terms commute. The other important term is this. Okay? So let me just spell out the two commutators that you need. One is ypz commutator with zpx, and the other is minus and minus is a plus, zpy commutator with xpz. Now, in order to use the fundamental commutation relationship between x and p, here you see that you have two objects and two objects. But there you have to use tricks like commutator of A and B, where A and B are two operators. With C, you can rewrite this as following, look at the trick. Just take out the A, B, C, plus take out the B, but at the end, so A, C, B. Okay? Now, this looks like a trick, but you can verify. It's just an identity. If you use this repeatedly, you could end up with, in the end, having simply object like xpx or ypy or zpz, which are IH bar. Okay, so you have to use repeatedly this trick. For instance, in a problem like this, you see that you can get the y and the px out of the game, and the only remaining thing is pz px. Okay, and similarly here, if you write this as minus x p z z p y, you see that once again you can get this out and leave only this there. Okay, and now we have minus x p z z p y. Okay, so these are just minus I h bar, and they're the same. So I just have I h bar from here x p y minus y p x. Okay, and this is nothing but LZ. Okay, as promised. Now, similar commutations are obtained for all the others, and in fact, you realize that behind everything here there is this vector product object, okay? And therefore, it's quite obvious to imagine that the cyclic combinations, so if you have y and z, here you will get I h bar Lx, and if you have z and x, you will have I h bar Ly. Okay? So in a cyclic way, they all appear essentially the same. Okay? Two consecutive ones are just equal to I h bar, the next one in the cycle, x, y, z, x, y, z. Is this clear? Okay? It's a simple, obviously you can verify probably in a more sophisticated way by writing this with the epsilon I j k symbol, but at this level there is really no need. Okay, although this might be useful. For instance, if you want to write this in one single expression, let me just write. Then you can write that, for instance, L component alpha, L component beta is equal to I h bar. You use the symbol alpha, beta, and gamma, L gamma, where this object is essentially the antisymmetric tensor. Totally antisymmetric means that it is just 1, -1, or 0. 0 whenever two indices are repeated, because it must be antisymmetric. So if you change, it should change sign. The property of this is that if you exchange two indices, you should change sign. Okay, so two indices cannot be the same. They must be 0 for two, and therefore the only non-trivial thing is this, and every other permutation gets a minus sign, and you have to count how many you have. So, for instance, epsilon 2, 1, 3 is just -1, while if you exchange also 3 and 1, epsilon 2, 3, 1 is again +1. Okay? So with this kind of object simplifies things with the so-called convention of repeated indices. So you have to sum here on gamma. And you see that you obtain exactly this object. Oh, by the way, I'm writing 1, 2, 3 instead of x, y, and z, obviously. Okay? So you can rewrite in terms of this object exactly the three rule given before. The same object, by the way, appears when you do vector products of just classical vectors. So for instance, if you want AB component gamma, okay, this is nothing but epsilon, alpha, beta, gamma, A, alpha, B, beta. Okay? So the ordinary vector product is also expressed in terms of this. And sometimes when you have heavy manipulation, heavy algebra, it might be useful, okay, to just resort to this object. Okay, now, it's not clear what variables enter in this object. In principle, you see there is coordinate and momentum. But I want to show to you that quite remarkably, but I mean quite remarkably from just a naive look, you might say, okay, everything enters. Therefore, theta and phi and r will enter in general, okay? Where theta and phi and r are now, from now on, I will try to write the system of coordinates that I'm looking at. Okay, so if I have any vector r, okay, this will be just parameterized by an angle theta. And if you just write this to be the projection on the x and y plane, so this is the projection there, and this projection is obviously making an angle phi with the theta axis. These are the standard spherical coordinates. And by the way, it might be useful to, in fact, if this is a circle, okay, there, to introduce three standard and fundamental versor unit vectors. One is r, which is simply r divided by its length. So this is a versor of direction of r and unit length. Okay? Another one is orthogonal to this and is essentially in the xy plane, okay, in the direction of the phi motion. So this is phi. Okay? I should draw it in principle all in the same place, but it's probably easier to. And another one has to do with theta, and so it's orthogonal to r and to phi, and it goes like that. Okay? So r, theta, and phi are three unit versors, okay, which are associated to the radial, theta, and phi direction. Okay. Oops, this is not useful. Now, you know to express the x, y, and z in terms of r, theta, and phi. I remind you here, x is just r times the sine of phi, sine of theta, and times the cosine of phi. Y is r sine theta times the sine of phi, and z is, the simplest one is just r cos theta. Okay? These are the standard rules. Now, you know also how to change variable, really, in the various derivatives. And for this purpose, I urge you to do an exercise that was included, in fact, in George Thompson lecture notes, but I ask you to redo it, please. One thing that you can quite easily do is the following. You notice that the derivative with respect to, I mean, it's simple to calculate derivative of x, y, and z with respect to r, theta, and phi, because you have the formulas there, so every derivative is immediate. The inverse are rather ugly looking, so if you try to express theta in terms of, or phi, or in terms of x, y, and z, they're ugly looking. They have inverse trigonometric functions, okay? But these are simple. So it's simple and direct to calculate, for instance, this object, or dy in the r, or dz in the r, or in fact any derivative, okay? So for instance, the d in the r can be calculated as the x in the r times the derivative in the x plus the y in the r times the derivative in the y plus the dz in the r times the derivative in the z. Similarly, for the theta, you have very similar expressions with here theta, okay? Let me not write everything. And for phi, you have also simple expressions like that. All right? Now, these are all simple. Okay? These are all simple. In particular, the derivative with respect to r simply erases the r everywhere. So you can even express it as x divided by r, and this is y divided by r, okay? And this is z divided by r. Okay? But even those are very simple. For instance, dx in d theta, well, it's simply a sine that becomes cosine when you take a derivative, okay? R, by the way, appears in every ingredient here. So, for instance, you have dy over d theta, dy plus dz over d theta, dz, okay? So you see that both these three objects here have all an r in front, okay? Because you are not touching r. You're taking derivative with respect to r. So it's best to divide everything by r. In this way, r is again cancelled off. And similarly here, if you take derivative with respect to phi here, for instance, what you have is, well, 0 in this case. Okay, so the third one is in fact not present because dz in d phi is just 0. Okay? You see, there is no phi there. The first two have derivatives of cosine and sine, but they have a common r and sine theta, which is everywhere. So it's this time comfortable to just divide everything by 1 over r sine theta. Okay? When you do this, you end up with an expression for derivative with respect to r, 1 over r derivative with respect to theta, and 1 over r sine theta derivative with respect to phi. You will find what? You will find, well, let me make more space, some coefficients here, a matrix 3 by 3, times the gradient in this form. Okay? The coefficients are just, can be determined by just taking the derivative. I write them for you. Okay? If you calculate all derivatives, you will obtain here sine theta times cosine phi, here sine theta sine phi, and here cosine phi, here cos theta cos phi, here cos theta sine phi, and here minus sine theta, and here minus sine phi, and cos phi, and 0. Okay? You might say very boring. It is very boring, but you should notice that this object here is just r, the direction of r. You see, it's this, this, and this without the r in front. Okay? Oops. I have it wrong. It's cos theta. All right? Okay? Let me check. I have not made too many mistakes. Yes. Okay. This second object here, you can quite easily verify is just theta, the direction of theta, the versor. And this third one, okay, it's simple to verify, okay, if this is just the point on the plane where this is just phi. Okay? So the 3 rows are just the 3 unit vectors of the new coordinate system. And this is the gradient in Cartesian coordinate, and this is the gradient in, well, it's not written very nicely. And this is the gradient in spherical coordinate. Okay? So the radial component is just d in dr. The theta component is 1 over r d in d theta, and the z and the phi component is 1 over r sine theta d phi. Okay? Good. Now, you can invert this. Okay? By the way, this is a matrix with 3 unit orthogonal vectors, okay, in rows, and therefore is an orthogonal matrix. So if you want to invert and get this in terms of this, it's very simple. You just transpose this matrix. Okay? The transpose of the matrix, so this coming into column, is simply the inverse that allows you to go from here to there. Okay? So you have now expressions which are pretty useful because you can express any derivative. So just to I write like this. Any derivative with respect to standard Cartesian components as the transpose of this matrix times the radial theta and phi derivative. Okay? Is this clear? This is just standard thing which you should have done and you have probably done, but let me just recapitulate to you the thing. Okay? So it's the transpose of this matrix that appears there. At this point, it's a pretty simple thing, okay, to, for instance, express the angular momentum in the following way. Let me just do the calculation where? Maybe here? Now, this is R, vector product, minus I h bar the gradient. Let me put this in front. Okay. Now, the gradient, okay, can be expressed in this new coordinate system. And in the new coordinate system, you can rewrite, it's a very simple thing. It's just R. So the gradient is an R component, which is simply d in the R, a theta component times 1 over R d in d theta. Okay, I'm simply writing this times the 3 versors plus phi times 1 over R sine theta d phi. Okay? These are the objects that you have. Is this clear from where it comes from? This is the gradient, but rather than written in Cartesian coordinate, written in the 3 fundamental objects that are these 3 things. This, okay? And the objects in front, I just read it from the matrix, are R, theta, and phi. Now, this is simply R times the direction R. And therefore, for instance, this object does not appear because this is vector product of R and R in itself. So this goes. So nicely, there is no derivative with respect to R in this angular momentum object. Also, you see this R appearing here cancels exactly the 1 over R and the 1 over R there. Okay? So nicely also, there is no R anywhere. And all in all, you can verify that R vector product theta and R vector product phi are just, well, you can calculate the two, are just the following thing. Minus I h bar phi times the derivative with respect to theta minus theta times 1 over sine theta, the derivative with respect to phi. Okay? So you can just calculate the vector products here, okay, in terms of the new 3 unit vectors, and the R has disappeared from anywhere. Okay? So this is the new expression for the angular momentum operator in coordinates theta and phi, in fact. R does not appear. If you put the expression for phi and for theta explicitly, you can obviously rewrite the 3 components explicitly. Okay? So it's a simple exercise which I ask you to do, for instance, to verify the following things. You can verify that Lx, the x component is just I h bar sine theta, the derivative with, no, sine phi, sorry, the derivative with respect to theta plus cosine phi, cotangent of theta, the derivative with respect to phi. Simply write these objects as x, y, and z in the x, y, and z components, which you read from here. Okay, for instance, x, y, and z component of theta are this, x, y, and z component of phi are this. Okay, so you split all the components and you read Lx to be just that. Ly has a similar expression with slightly different ingredient here. There is a cosine of phi, d in d theta, and here there's a sine of phi, and again a cotangent of theta, d in d phi. And the simplest one is Lz, okay, which is minus I h bar, the derivative with respect to phi. So Lz is just related to taking derivative with respect to phi. Lx and Ly have fairly more complicated expressions involving derivative with respect to theta and phi both with trigonometric factors in front, okay? So this is a quite simple object that you can write. The main important thing is R does not appear at all, okay? So it is all related to angular variables. This is also a very simple thing to remember, by the way, okay? It looks like a momentum in the phi coordinate, right? Minus I h bar, the derivative with respect to phi. So z is pretty simple to remember. Okay, another important object that you can construct is the square of L. So Lx square plus Ly square plus Lz square. This is an operator again. The square of this plus the square of this plus the square of this. You have to be careful, obviously, in squaring those things because, there are derivatives and therefore you have to account for them properly. This total angular, this is called the total angular momentum, or L square usually, has obviously a certain expressions in terms of theta and phi, which I report in the notes, but is not particularly important to us. There will be second derivative with respect to theta and so on and so forth, but not particularly important. What is important is that this object commutes with any of the three individual components of the angular momentum. In other words, you can verify, for instance, that so L square commutator Lx, for instance, is equal to 0, and the same for Ly and Lz. The calculation is simple. You don't even have to use really the explicit expressions with theta and phi. Actually, it would be very, very ugly to perform this calculation by just using the explicit expression. In fact, we will make a very, very sparse use of this. Probably in one case, I will ask you again to resurrect these formulas, in particular to sum these two with an I in front, when we will construct spherical harmonics. For the rest, you might even forget about them, okay? We'll never use them. Important, however, is to remember that there is only theta and phi there. Okay. So I don't do the calculation of this by using that, but I directly use the commutation relationship. And the thing is very, very simple. So this is just the commutator of Lx square plus Ly square plus Lz square with Lx. Okay? Now, certainly Lx commutes with Lx square. Okay? So this is not important. But the other two have Ly square commutator with Lx and Lz square commutator with Lx. You might say, okay, these are different from 0. They are, however, canceling each other. For instance, here you can take off one of the Ly and write this as Ly commutator Lx. And here you take off one Lz and you write it as Lz commutator Lx. Now, this object here is essentially this, just turn. So there is a minus sign. So this is minus I h bar Ly Lz. Okay? And this is directly this object. So it's plus I h bar L z sorry, I'm making LZ, LY. Did I think I missed something. Huh? Yes, yes. When I do this commutator, sorry, I should be careful. I should exit this from the right, and I get this plus, good point. You see, I mean, you can miss terms by being too fast. Plus this object, okay? The rule that I wrote is you have to exit on both sides, okay? And similarly here, I exit from the left plus a similar thing, okay, where I exit LZ from the right. Okay, thanks. Okay, so if you include all of these four terms, now you easily verify by using the fundamental thing that the result is just 0. Okay, let me not just stress any further the very simple algebra that is behind this. Okay. Good. So, why is this useful? I mean, after all, it seems to be unrelated to our original problem. I had p square here. Why I'm stressing so much L and its properties, commutation, and all this ugly and boring change of variables? The reason is that L, in fact, L square, this object here, is really hiding into this operator there. Okay? We will see, we will fish him out in a second. And by using the fact that I can actually construct eigenfunctions, so functions of theta and phi, which are eigenfunctions of L square, I can really separate variables very effectively. You already have encountered this in the first course on quantum mechanics. These are the spherical harmonics, okay? So L square and, for instance, LZ commute. So you can take these two to be a pair of commuting operators. LZ doesn't commute with Ly and Lx, so you cannot construct common eigenfunctions to all four things, but you can construct common eigenfunctions to L square and Lz, for instance, and these are the so-called spherical harmonics, okay? So these are eigenfunctions of L square and Lz with certain eigenvalues, okay, which are given by essentially L plus 1, where L is an integer, and M, where M is also an integer running between minus L and L. We will see this more later on. For the time being, I'm trying to put this thing in perspective and see that this is useful because I can construct eigenfunctions of them. So let us return to our main point. Where is L square in P? Now, classically, it's pretty simple to express. So if I have a particle, okay, with a certain, say, momentum here, at a certain distance r from the origin, it's clear that the angular momentum squared is simply equal to what? It's r squared times the perpendicular component of the momentum squared. Okay? Remember, classical physics is just the product of the two. But now this you can write as p squared minus the parallel momentum squared. Okay? This is all classical physics vectors. Okay. Now, you can also rewrite this as r squared p squared minus, you see R, the component, the parallel component is what? Is R dot P, right? Square. Are you satisfied with this? So the square of the angular momentum is just R square P square, where this is square of full vectors, okay? I'm not indicating the vector thing, minus R dot P square. It's very simple. Now, unfortunately, these are quantum mechanical operators and not just ordinary vectors, and therefore this equation is almost right. There is an extra piece here, and the extra piece is R square P square minus R dot P plus I H bar R dot P. Okay? One extra piece of this, linear, however, this is square, with I H bar in front, which you could expect. Okay? This is purely quantum mechanics, and therefore, if you set H bar to 0, it should disappear. Okay? Now, how can I prove this? By the way, consequence of this is that now P square, which is the object appearing there, okay? Don't be misled by the fact that I don't use the arrow from some time, okay? Just for typographical reasons, okay? So P square that appears there, you see now, I could express in terms of L square. If I divide everything by 1 over R, by R square, I can rewrite this as P square equal to L square divided by R square minus 1 over, plus, I bring this on the other side, plus 1 over R square R dot P square minus I H bar over R square R dot P. Is this clear to everybody? Okay? And now, careful, L square, I know, it's all theta and phi and derivatives, now R. You might be still worried about these two objects. These objects, in fact, do not have theta and phi. It's very simple to show, okay? So let me show this, and then I return to this main thing, which I haven't proved yet, okay? Now, let us see. If I have a derivative with respect to R, you know I can calculate it as the x in the R, in the x, plus the y in the R, d in the y, plus the z in the R, d in the z. Okay? But these, remember the expressions, x, y, and z have a prefactor R, all of them, times, cosine, and sine. Okay? So when I take a derivative, this is simply x over R. Similarly, this is just y over R. And this is simply z over R. Okay? So if I multiply everything by R, this go, the expression I have is x times d in the x plus y times d in the y plus z times d in the z. Put a minus I h bar in front, okay, and what you get is this times minus I h bar. You can immediately recognize that this is just a scalar product of R and P, x px plus y py plus zp. Okay? So R dot P does not contain any theta and any phi. It's just a simple radial derivative. Okay? So this is what appears there and there. Okay? So now it's more clear, hopefully, that P square, the Laplacian in 3 dimensions, has been kind of split a little bit more neatly into radial parts and an angular part divided by R square. Okay? This makes the separation of variables quite neat, not of the same level, just some of things, but very, very useful in solving the problem. Okay? So all I have to really show is that this is true. There is this extra term. Now, this was one of the exercises you had in the first part of the course. I think I have even the references. Exercise, I forgot. It's one of the exercises of chapter 11, I think, of George Thompson thing. Okay, it's in some sense boring, and I don't want to really do it for you. I indicate as an exercise also in the notes, and so this is, let me just say that this is minus h bar r in the r. And all you have to do is, for instance, L square, you write it as L component alpha L alpha, okay, summed over alpha. But every L alpha, you write it as epsilon alpha beta gamma, okay, R beta P gamma, and the other also epsilon alpha beta prime gamma prime R beta prime P gamma prime. You do something like this, okay? Then you use an expression for the product of two epsilon objects, and this is a quite simple thing to understand. These are 1 or minus 1 or zeros, okay? So the result must be just 1 minus 1 on zeros. And in fact, you can very easily see that since I am summing of this alpha, there are only two possibilities for beta prime, gamma prime, and beta gamma. Either beta is equal to beta prime and gamma is equal to gamma prime, okay? They must all be different, remember, because this is antisymmetric, okay? So this is one possibility, and it's a delta of beta, beta prime, and delta of gamma, gamma prime. The other possibility is just the exchange of one. But since there is an exchange, there is a minus. So delta beta gamma prime, delta gamma beta prime. Okay? Now, if you rewrite the sum over this over alpha in this way, then you can pretty much reduce your object to things that if you then use the appropriate commutators, because remember that, for instance, the first term, okay, you would have beta equal to beta. So you would have things like R beta, P gamma, R beta, and P gamma. Before you write into something like this, which would be tempted, obviously I have repeated index here, and I have to sum over them. Okay? So this would be my R square if I sum like that. But before you do that, you have to remember that this has to be commuted. So you have to play a little bit with commutators, and once you do it, you get this famous object there. Okay? And obviously there are all the others, this one. Okay? So play around with it a little bit and make yourself happy with this formula here. Okay? All right. Yeah, the other term would be minus R beta P gamma R whatever gamma P beta. Okay? So these two terms, all in all, if you rearrange them appropriately, generate this object there. Is this clear to everybody? If so, let us proceed, because now this expression here, by the way, this expression can be written in a slightly simpler way. You see, I have a second power of this object and the first power of it. You can write it in at least two possible ways. One way is L square over R square minus h bar square over, no, sorry, second derivative, minus 2 h bar square over r first derivative. Okay? They have both second and first derivative because, I mean, after all, you have this object there. Another possible way of writing is L square over R square plus the Hermitian relative radial momentum, PR, which George Thomson has introduced for you. Okay? So this object is PR, is just minus IH bar, not simply the derivative, but there is a plus 1 over R term to make it Hermitian. Okay? So you can rewrite this thing in several possible ways. It doesn't matter. The important thing is that the variables are very nicely separated, R and theta and phi. Okay? So let us proceed now with the separation of variable for our problem. Oh, one comment. Strictly speaking, this is not purely quantum mechanics. This is just a Laplacian in spherical coordinates. So it happens, for instance, that you use similar object, apart from the h bars, obviously, in writing the Laplacian for electromagnetism, for instance, in solving Laplace equation in a spherical coordinate. Okay? So once again, there you use spherical harmonics. So this is pretty much more general than just what we will use it next. Okay, so now let us proceed, and the separation of variables proceeds in the following way. Rather than using psi of r, let me try a function that is a radial function of r times a function that has to have nice properties. In particular, it must be an eigenfunction of L square. You see that L square appears there. Okay? So let us take spherical harmonics, which we will learn more, but you already know, are eigenfunction of L square. So generally speaking, this object here, you see now I am starting to specify what n is. Certainly it has to contain these integers L and M that appear in the spherical harmonics. But more than that, it should also, in principle, have some other index. We will see that the radial part should depend on L for sure, and possibly, because you want to have freedom of many possible radial functions, another index k. We will see that M does not appear in a second. Okay, so let us use that. You see that this object here, I just divide everything by twice the mass, twice the mass, twice the mass, well, whatever here. Okay, so I use that expression, and I have something like, let me write it for you in detail. I have minus h bar square over twice the mass times the second derivative with respect to r plus twice over r the first derivative with respect to r. This is essentially these two pieces. Multiplying r and y, okay? Then I have the other term that is plus this object here, or that. But this I know that when acting on the y part makes a simple thing, right? Makes simply a constant, okay? So plus, I write h bar square from L square times L plus 1 twice the mass r square, and the same thing, r, k, l, y, l, m. Okay? So this is all I get from this rewritten in this nicely separated form. Okay? Then I have this. So I have minus z e squared over r times r times y. And then I have equal the energy, which in principle should depend on L, M, and whatever other labels I have there. We'll see that obviously it's simpler than that, times R, K, and Y, L, M. Is this clear to everybody? By simply choosing the wave function to be a radial function times the spherical harmonics, which are eigenfunction of L squared, I have written this in essentially using the eigenfunction property in this way. Okay? If it is clear, I proceed. Because now you see that YLM does nothing. I have already used the fact that it is eigenfunction of L squared and appears everywhere as a spectator. By the way, you see that since L squared appear, which is given by L plus 1, where L is this integer, which we will discuss more in the rest of the lectures, M does not appear anywhere, okay? And therefore, this is the reason why the radial function will not depend on M, because M really does not appear, okay? And by the way, for the same reason, the energy will not depend on M at all, okay? So, all in all, I can just cancel the Y because it has played this role. And now would be only a spectator. Okay? So, you see that I have reduced with this trick the problem to a radial problem alone. The angular part was trivially solved by the spherical harmonics, which is a considerable simplification, you have to realize. From a three-dimensional differential equation, I have reduced myself to a one-dimensional differential equation, which in principle I can solve on a computer, for instance. By the way, if the potential was not exactly this, but was another central potential, V of r, then all the steps done until now would be identical. What is different is that I cannot solve in general a V of r of generic form analytically, okay? And in general have to resort to a computer. But solving a radial problem alone is infinitely more simpler than just solving a three-dimensional Schrodinger problem, okay? So in any case, exploiting this symmetry of angular momentum considerably simplifies our problem, okay? So let us just copy back that equation and observe it for a second once more. So it's minus h bar squared over twice the mass, second derivative with respect to r, plus 2 over r, derivative with respect to r, which in general will depend on some further label k from L, plus h bar square L plus 1 divided by twice the mass r square minus z e squared over r times r equal to E times r. Okay? So this is our object. Oh, let me erase quite a few things. Okay, so questions until now? Erase here. Okay, these are obviously function of r. Now, by the way, this is nothing but the radial Hermitian operator, divided by 2m. Okay, you can verify very easily. This object here, you see, it looks like a further potential term. This time positive, and in general, if L is different from 0. By the way, L, the theory of angular momentum tells me that L can be 0, 1, 2, any positive or 0 integer. Okay? So this is a positive repulsive potential, okay, which you could associate to a centrifugal type of barrier. Okay? And goes like 1 over r square, as opposed to the 1 over r appearing in the Coulomb potential. So close to r, close to 0, it dominates over this. Okay? So the full, the combination of both, when this is present, is really a potential of this type. When r is very large, this is much smaller than this, and therefore here, eventually, it's Coulomb-like. Okay? So it is pretty similar to the potential I was drawing last time. But this time, I don't have a particle sitting here in the minimum. It's a more complicated problem. In any case, I have to find the bound states. I have to find the bound states of this potential here in this special Laplacian problem. Notice that as opposed to the standard one-dimensional problem, where I would have something like this, here what comes from the Laplacian is more complicated. There is also this term, which makes it slightly more inconvenient. Also, the radial function has to be normalized in the following way. Remember that you have integral over r square. Then I have an integral over theta and phi. So I have an integral, for instance, over phi from 0 to 2 pi, and an integral from the theta sine theta from 0 to pi. And then I have r square in the integration measure. And then I have the square of r times the square of theta and phi thing. Okay? Now, by definition of y, the angular, the spherical harmonics, they are normalized in such a way that this angular integral is just 1. So, to normalize the wave function, I have to require that this integral, okay, is also 1. So you see, once again, a normalization that involves an r square rather than just the wave function square. Okay? So this is the two crucial difference with a standard one-dimensional problem on the half line, because here I have from 0 to infinity. Okay? Now, luckily enough, this is also the clue to what we should do. And the thing to do is the following. Define a new variable, a new function, u of r, u of k and l, which is simply r times the radial function. Okay? You see that r is what accompanies the radial function in this normalization. Okay? So just put it in front and call the result u. Now, with this, it's very simple to show the following thing. The second derivative of plus the first derivative term calculated on r, so this object here, is nothing but 1 over r, a simple second derivative of u. Okay? It's a very, very simple exercise. Just try to do. Okay? You can do it in many ways. Either you substitute here r equal to u over r, or vice versa, calculate this, and just verify that this is true. Okay? So in some sense, this simplifies things in a considerable way. First of all, the normalization now is integral from 0 to plus infinity in the R u of R modulo square equal to 1, which is the standard normalization you would write for a particle in 1D. Okay? Second, this piece here, okay, this object, in terms of u, it appears now simpler. Why? Look, this object is minus h bar square over twice the mass. I told you it's 1 over r, second derivative with respect to r of u, plus this object is exactly the same. Okay, I could copy it, but I don't. And here I have r, which is u over r again. And the same appears for E, which is u over r. Okay? I have substitute wherever I have r, u over r. And now you see that this 1 over r, which appears there, is in fact going away. Okay? So, in conclusion, hopefully it was clear that the use of this variable u considerably simplifies the equation, and you have the following object. Second derivative with respect to r of u, kl, plus this object equal to this object. Okay? With the standard normalization that I indicated before, integral of u equal to 1. Now it looks really like a one-dimensional problem, okay? For the function u, with this effective potential that is depicted there. Obviously, if L is equal to 0, this piece is not there, and this is simply the Coulomb part. Okay? So this is for L equal to 0, and this is for L greater than 0. Okay? Is this clear to everybody? Okay. Now, the equation is still full of h bars, m's, the mass, E, the charge. As I showed to you last time for the harmonic oscillator, we should get rid of those constants, but not just putting them to 1. Or, I mean, if you have enough experience, you can do that. But I encourage you to, the first times you do these things, to do it slowly, and again to try to define your unit of length and unit of energy in a clear and consistent manner. Okay? So what we did for the harmonic oscillator, we will repeat it here. Essentially, I will say the following. Suppose I have a length A. This length, for instance, determines a certain energy. Z E squared over the length is the Coulomb energy associated to a certain length A. Let us determine the length in such a way that the Coulomb energy exactly matches the confinement energy h bar squared divided by mu A squared. Okay? So this one. Notice I omitted the factor 2. I did it on purpose. I might include it. I mean, if I want to define an A, I could include a factor 2 and proceed consistently. But the quantity I would get is not the standard ball radius. It differs from the ball radius by something, by some constant. Okay? So I don't do that. The deep reason behind it is the virial theorem. Okay? Kinetic energy and potential term in the oscillator problem are just related on average by just the same quantity. Here there is a factor 2 difference, and therefore this is not present there. In any case, I don't want to make it too long. Just solve this equation. Okay, so suppose I have that object and you want to say, okay, what would be the natural length there? Well, let me define z e square over a equal to h bar. Then you solve it. So you multiply, for instance, you take off this. So a equal to h bar square divided by mu e square times z. Okay? Now, you have certainly seen this before. By the way, I'm writing mu to be the reduced mass, which is slightly different from the mass of the electron, okay? Because of the mass of the proton, but it's almost the mass of the electron. So if you have seen this before, this is just the Bohr radius, okay? But this is now the Bohr radius divided by z, because I have more charge, and therefore the natural unit of length is actually small, okay? More charge means a deeper Coulomb potential means that everything gets squeezed close to the nucleus more, okay? So it's reasonable that the unit of length, which is this effective Bohr radius, is really divided by z. Okay. What about this quantity itself, okay? So in fact, let me call this, so this would be the, I think I insist in calling this a Bohr radius. So this is the Bohr radius for z equal 1 divided by z, okay? So let me call this still effective Bohr radius AB. Now, the energy associated to the left-hand side would be this, okay? And let me call this my unit of energy. How much it is? Well, let's see. Put AB there, so this is z e square. I have h bar square times mu e square z. So let's collect things. I have mu e to the fourth z square divided by h bar square. Now, this quantity, you also have seen it before. It is called the Hartree. Okay? Numerically, if you calculate, is first of all, it goes, you see, it goes with the fourth power of the charge and with the second power of z. Okay? So numerically, this is equal to z square, okay, times something that is close to 27.2 electron volts. The electron volts are the very good units also that you could use in atomic physics, okay? But an even better unit is the Hartree, okay? So in fact, atomic physicists use atomic units for which the unit of energy is just this. We'll see that the hydrogen atom ground state is half the Hartree. Okay? It's called Rydberg also. Okay? But the Hartree is in fact the natural unit of the atomic units. Okay, so I have the lengths, I have the energy. I could define everything in practice in terms of this object. So for instance, whenever I have a length, I want to divide it by the unit, the Bohr radius, okay? And I could define this to be a dimensionless length. And then, obviously, I could fish out factors h bar over mu Bohr radius everywhere. By the way, in order to really be consistent with this, you see, if I put here a factor AB, I really have to rewrite this as integral from 0 to infinity in d rho, and the new function u tilde of rho has a factor square root of Bohr radius in it, okay? Because it comes from there. So u tilde, I define u tilde of rho to be square root of Bohr radius times u calculated at the position, obviously, AB times R. Okay? So this is my new function. This is my new length, And in terms of this, you might be surprised, or maybe not, to discover that the equation is extra simple. Let's see. It looks like the following. From here, I have minus h bar square over twice the mass ball radius square, second derivative with respect to rho, u tilde, okay? Well, you might say there is a square root. Yes, but the square root is everywhere. The equation is linear, so I can forget it, really, okay? So it's only, I mean, to be precise that I put it there, but it makes no difference in our equation whatsoever, okay? So plus, and you recognize here this quantity, because this is equal to that, obviously, by definition, okay? So this is really, I could rewrite it as minus the R3 over 2 plus, well, once again, here I have h bar square over twice the mass ball radius square L plus 1 divided by rho square, okay? And once again, here really I have the R3, so let me write it as the R3 over 2 minus z e square over ball radius rho, and this is again the R3, so R3 over rho. And this is u tilde. And this is the energy, u tilde. Okay? So I fished out all the constants and introduced the dimensionless length. Now you see that if I define, I can divide everything by the R3 in the following way. Okay? So the units of energy just divide the full energy. Okay? So if you want, this is the dimensionless energy. The energy divided by the R3. Okay? Now, in this new system, probably see how neat it is. There are no h bars, no masses, no z, no e. Huh? The only thing that appears are just 1/2, 1, L plus 1, obviously, okay? And everything is dimensionless, okay? So it's as if I had put everything to 1, except the 2, obviously. And, however, you know how to reconstruct everything, because if I tell you plot this function and tell me how much it is 3 angstrom away from the origin, you know that, well, you have to, again, use the relationship involving the ball radius, which you can calculate how much it is, and so forth. Oof, I've been very slow. I'm sorry. Okay? So is this clear to everybody? So the next thing we want to do, and once again, much of what I have done is, strictly speaking, although I should probably define different lengths and things, also allowed for a central potential more generic than the Coulomb part. What is, however, very specific is that this term now is 1 over rho, or 1 over r, and we will make an explicit exact solution of this next time. Now, the exact solution is in terms of hypergeometric series, you know, this confluent. But I must confess my profound, whenever I see an hypergeometric series, I do not have a big intuition of it, okay? This is my limitation, obviously. I know what an exponential is, but if you tell me plot an hypergeometric series, I have to run to a computer and see if Mathematica plots it for me. So also I do not encourage too much, obviously, my students, because of my personal ignorance, to really rely on very abstract, objects that are special functions. So I ask you really to do things with your hands, okay? You should be able to just do things by just re-getting the things independently of the fact that in some books on special functions, everything is just written in detail. So we'll actually do this problem without the Kummer equation and the hypergeometric function, okay? We do it from scratch, from the beginning, and see how the solution comes out and how the quantization comes, okay? So this is probably a bit redoing things because you have seen this already, but I think it has some degree of, pedagogical usefulness, okay? Because it shows how to do things explicitly with your hands. But we will do this next time, okay? So the plan for next lecture is the following. First of all, start to understand what this equation tells you about the limits that you have for rho going to 0 and for rho going to infinity. I might call again R, okay, but I will probably use still the notation rho to mean that I have get rid of all the dimensions, okay? So there are simple arguments that you can make to tell me how the function u tilde should go for rho going to 0 and for very large distances. And we will see that this is the fact that for very small distances, this should go like rho to the power L plus 1, where L is whatever appears there. And that for very large distances, u tilde should go like e to the minus some constant times rho. So in an exponential dying way. And by the way, this constant is directly related to this, okay? This is very simple to show. Both things. We will do it first thing next time, okay? So show that what controls the decay of the function is just the energy, which we still don't know, obviously, okay? And close to the origin, L commands a behavior like rho to the L plus 1. Once I know these two things, the idea is the following. I don't know how the function is, but I know that it should start from this. I know that it should have this, okay? Let me put some expansion there. So 1 plus some coefficient, okay? Let me call it whatever, C0 plus C1 rho plus C2 rho square, okay? A power series. This is certainly the most general thing that you can do if you know that these two things are there. And then the solution is the following. Just try to put this thing into the equation and try to see if you can determine some recursive relation between these coefficients. And you can do it, which is a trick, by the way, that is useful in other contexts, okay? You have a differential equation. You try to see what you expect for the large distance and small distance behavior, and then you try to solve it recursively. This is probably how Kummer solved first his equation by just and found the hypergeometric series. I suspect. I mean, I don't know exactly, but this is a standard approach, I believe, which you should learn and learn how to do it yourself without reading the solution in a book. Okay? So this is what we'll do next. And we will find that only some specific lambda are admitted, okay? Which are the bound states of the hydrogen atom. Okay, so we'll do it next time.